Hello everyone, I hope you're doing well. In today's video we are going to discuss about low density parity check coding or LDPC. So let's move on to the video. First of all, we are going to discuss about what error correction coding or ECC is. ECC are the means by which we compensate for the corruption that occurs in the communication over imperfect channels. The diagram given below is just a simple graphical illustration, but if we talk in the detail regarding ECC, the network 1 will first send a message. This message then passes through the encoder and is converted into a specific code word. Here in this diagram, this binary signal represents the code word. After that, the channel then modifies the code word by adding noises or bits. These are the noise channel that has been added to the signal. These noise then passes through the decoder on the receiver side, which uses the noise signal to guess which code word was transmitted by the transmitter, and then it gives the output on the network 2. Much of the research work on ECC is devoted to in improving the probability that decodes whether the guess is correct and also the complexity. Now let's move on. Now we are going to discuss about what parity bit is. Parity bit, also known as check bit, is a single bit that can be appended to a binary string. It is set to either 1 or 0 to make the total number of 1 bits either even or odd parity. The purpose of the parity bit is to provide a simple ways to check for errors later. When data is stored or transferred electronically, it is not uncommon for bits to flip, change from a 0 to a 1 or vice versa. Parity checks can detect some of these errors. For example, to check a binary sequence that has even parity, the total number of ones can be counted. If the number of ones is not an even, an error is likely to have occurred. We will see it more in the next example. Here you can see that there are 4 columns. The first column represents the original data. In each data there are a specific number of ones and zeros. For parity bit checking, we are going to check the number of ones. In the second column, as you can see, it is representing the counts of ones in the original data. In original data 1, there are, as you can see, 1, 2, 3 and 4 counts. So it has shown 4. In the second original data, there are 3 ones, and in the third original data, there is only 1, a single one. So if we are applying even parity, we are going to check whether the number of ones are even or odd. If the number of ones are even, then the even parity check will give the result 0. And if the number of ones are not even, it will give the result 1. As you can see, is the first original data, the number of ones is even, so the even parity is giving us 0. While in the second and third data, the number of ones is odd, so it is giving us the output 1. And the reverse case is for the odd parity. If the number of ones are even, then the odd parity will give us 1, and if the number of 1 is odd, then the odd parity will give us 0. So now let's move on to the next slide. Now we are going to discuss about difference between error detection and error correction. Error detection, it involves checking whether any error has occurred or not, while in error correction, it involves checking as well as correcting the error. In error detection, the number of bit errors and error type doesn't matter, while in the error correction, number of error bits and error types does matter. The reason is that error detection is only used to detect the error. It doesn't have any concern what to do with the error bits or type. But for the error correction, we need to know what kind of error bits and error types are generated. Let's move on to the types of the error detection and error correction. The type of error correction are parity check, checksum and CRC, while in error correction, the types are Hamming coding, Reed-Solomon coding and low density parity check coding. Our main concern is low density parity check coding, but for that we are going to discuss what is Hamming code first. Hamming code is a set of error correction codes that can be used to detect and correct the errors. It occurs when the data is moved or stored from the sender to the receiver. It is a technique which was developed by R.W. Hamming for error correction. Now I'm going to discuss the example of Hamming coding 7.4. First of all, we are going to give 4 bits to the data message. After these 4 bits are given, they will be divided into 3 different combinations as given in the code word. The code word will define the other 3 parity bits. As you can see, x5 is representing u1, plus u2 plus u3. In this given formula, the plus is acting as an XOR. As you all know that if both the bits are of same number, either 1 or either 0, then the result will be, if both the bits are same, either 0 or 1, the result is going to be 0, and if both are different, then the result is going to be 1. So on the right side you can see that there for each 4 bits they have assigned 3 parity bits. Now as you can see there are a total number of 7 bits. So if we consider the 7 bits combination, there will be 128 combinations, but out of 128 combinations we are only taking 16 into consideration for the Hamming code 74. After that we are going to discuss about the low density parity check coding.
What is LDPC? LDPC, also known as low density parity check code, is a linear coding correcting code method for transmitting of messages over a noisy channel. As we progress in our wireless communication and technology, there is a need for a more robust and a quick way of coding and decoding our errors as we transmit our data over any source of medium. If our data is noisy and we cannot decode it on the other end of our receiver, then it is of no use to us. Similarly, LDPC code is also one of the most used error correcting codes. Now we will see why do we use LDPC. LDPC is also one of the most commonly used in 5G. We will see why are we using LDPC instead of Hamming or any other codes. For example, let's take Hamming. Hamming is used to represent a parity bit for the protection of any data that is to be transmitted over any sort of medium. For example, if there are even number of ones, we will replace it with a 1 parity bit, so we will know there are even number of ones in the data. But there is a problem. If there is one corruption in the data, if one of the data is missing or is corrupted, then it can be replaced by looking at the parity bit. But for example, if there are more than one data bits corrupted, or we were not able to decode because of some noise, then we cannot decode it, because only one parity bit represents one correction or one bit of data. So to solve this, we will increase the number of parity bits, and it will come to a point that in Hamming code we will have to repeat our data bits exactly the same in the parity bit, and that becomes a hassle. It's like repeating yourself over and over again so someone can understand what you are trying to say, which is not feasible, because increasing the number of parity bits is not a good solution, because we are not protecting our parity bits. Our parity bits might also get corrupted. When our parity bits become corrupted, we cannot decode our data stream or data bits that we are going to transmit. So as I mentioned earlier, we use LDPC for the protection of our parity bits as well as for the protection of our data bits that is to be transmitted over any medium. As you can see from the diagram, the number of bits are connected to 4 of these blocks. What does this mean? In 1950, Hamming came up with an idea that was to solve this problem. He said if we group a number of bits and connect it to a group of parity bits, then we can achieve our desired result. Meaning that if different combination of bits, for example 3 or 4 of these bits are connected to one of the parity bit, then we can use less number of parity bits and have the same desired result as Hamming code. So basically what Hamming was trying to say was, if we have a combination of bits designed specifically for a parity bit, then we can solve these combinations to get our missing parity bit or missing data bits. As Hamming told us that different combinations can be used for the solution of parity bits and for finding parity bits or data streams that went missing or were corrupted. But there is a problem, and that problem was when we made different combinations with a number of parity bits, as you can see in blocks down below. The number of time consumed for the solution or for finding of missing parity bit or data bit was too high. For example, the combination became complex and it took more time to solve these missing parity bits or data bits to find our desired result. It was not necessary. So that's why we come to our matter at hand. Why is it known as LDPC? LDPC basically means that we should decrease the number of combinations allocated to a parity bit or a block, as you can see, to reduce the number or time used for solving for the missing parity bits or corrupted parity bits or data that we are trying to retrieve. Because for a computer it is more easy to solve small simple problems than large complex problems. For example, if you give a computer a more complex problem, then it will take, for example, 10 minutes, but if you divide that complex problem into 10 easy steps, it will do it in a matter of minutes or seconds. So basically what we're trying to do is reduce the density of the combinations of parity bits and data streams, so we can solve our problems, decode and code our LDPC codes easier and quicker. As you can see, these blocks are connected to maybe 10 or 9 of these bits. So as we seen before, the number of density or the number of combination here is large. To solve this one bit, we'll have to go increase all of these combinations to get our desired result, which is a hassle. Or we can just make a smaller combination with the bits and get our result faster, quicker and easier. So basically what we're trying to say is that LDPC is a combination of bits to a parity bit or as represented in the block, but with low density. So they came to known as low density parity bits. They were discovered in 1960 and are still used for 5G because of its protection of parity bits as well as data bits at the same time. The combination of different bits to the parity bit was a difficult objective. So to combine different parity bits to a bit, it became a very big hassle. So what we did was randomize the combinations. It was a more easier and it was more secure, more practical, and it took less time to solve and combine data bits with the parity bits. So we used random LDPC parity bits in our communication instead of combining one bit at a time to the parity bit. Now let's see this with a simple example. For example, if this was our received result, what will we do? How will we find out that what our data bits were? To understand this, we will see how these different combinations are connected to the parity bit. How are we doing these different combinations? For example, to know the location of these two unknown bits, we will see different combinations that are connected here. So let's see. We should remove all the unnecessary data to see more clearly and understand how we can solve these. For example, if we look at this block, it is connected to the first and the second last bit, showing that there are two number of ones in this data. So that means there will be a 0 in this location to give us the even result. Similarly, if we see at this block, it is connected to the last of the 2 bits and to an unknown bit, showing that these two are also even, so the desired result here will also be 0. So giving us the outcome of 1 0 1 0 and 1 1, which is our desired result, and this data streamed over any medium and decoded. As we see code rate, what is code rate? Code rate is basically number of bits over the number of transmitted bits. For example, if we have 6 bits, then we have 12 bits in Hamming code, giving us the code rate of 50%. As the code rate decreases, our protection increases, and so is the cost and expense of transmitting the data over a medium. For example, increase in the number of bits transmitted equals to increase in the number of expense that you are going through to transmit these bits. For example, if you decrease the transmitted bits, and so on, and your expense will be a lot less. So what we want to do with LDPC is decrease the cost, but do not increase the protection of the data bits and the parity bits. And we simulated our result in MATLAB Simulink. As you can see that our transmitted data and our received data are the same. We used an LDPC circuit simulation for this. For example, we added a noise in our input data and then decoded it using LDPC to achieve our desired result at the output. As you can see, the data stream that we sent and that we received at the receiver end are the same. And we can also see by the scatter plot that our reference output and our desired output scatter plot in XY plane are the same.